Okay, I'm standing in for Tony Farrell, who gave a talk yesterday on large-scale structures. I'm going to take that a little step further by talking on streaming motions of galaxies. So not just large-scale structures of galaxies, but large-scale dynamics of galaxies, the flow of galaxies on large scales. And it's a study I've been working on with Tony Farrell at UCT and various other people, René Kraan-Korteweg particularly. And it's the large-scale structures, large-scale dynamics, and in particular the Great Attractor, which is a very large overdensity of galaxies in our nearby universe, found in the late 80s by many people looking into the streaming motions of galaxies. And only recently do we have a complete picture of what actually the Great Attractor is. So those are the three main topics of today's talk. This is just a picture of a galaxy, NGC 4414, taken by the HST. Which comes back a little bit later as well, when we talk about the Great Attractor. One thing, I'm just taking little steps outwards. I don't know how familiar you are with the distance scales and megaparsecs and distances. So this is just our solar system here, the sun and all the planets. From us to the sun, it's 8 light minutes, or 150 million kilometers. So I'm just converting kilometers to light seconds, light minutes, to light years, to megaparsecs, which is the unit that we use for the distances to galaxies. So you've got the solar system here. Then here, I don't know if you can see it, but this in fact is the Southern Cross, and the 2 pointers there. This is the nearest star to us, Alpha Centauri. Distance is 4.3 light years, or in terms of parsecs, our distance, 1.3 parsecs. That's the nearest star to us. So if you leave the solar system, Alpha Centauri will be the next in line. Then if you look from above onto the galaxy, which we can't do because we're actually inside our own galaxy, this is a rough picture that you would have. The sun away from the center, distance to the center of the galaxy, roughly 8.5 kiloparsecs, 8,500 parsecs. And the sun goes around the center of the galaxy with about 220 kilometers per second. So that's just our local reference frame. We are roughly here, going around our sun. The sun goes around the galaxy at 220 kilometers per second. So I'm just stepping further and further out. If you go further out, you can see there are many other galaxies. This is just a compact group, the Higgs Compact Group 87, at the distance of 128 megaparsecs. So 128 million parsecs now. So we're going further out in the universe. And you can see that galaxies are very sociable. Many have neighbors. They have got, our own galaxy has the Magellanic Clouds around them. They are satellite galaxies to us. These galaxies, you can also see the different morphological types. This is a nice spiral galaxy, an elliptical galaxy here. These are different sort of galaxies containing different stars. The elliptical galaxies mostly have old stars, are very evolved, whereas in the spiral galaxies, young stars are being formed continuously. But you should see the universe is a very friendly place. All the galaxies within 2 megaparsecs, almost every galaxy has a neighbor. Now, there are very dense clusters of galaxies as well. This is taking it to the extreme. This is, again, a picture with the Space Telescope, Abell 1689. It's actually off the screen, but it's at a distance of 785 megaparsecs. So we're almost 1 billion parsecs now away from us. And it's a very dense, rich cluster of galaxies, centrally condensed. And if you look very well, it's a bit light, but if you look well, you can see these arclets here. And those is what's called lensing, strong lensing. So what happens is there's a galaxy in the background here. This is just a schematic view. There's a galaxy in the background. We are here. And this is so massive that actually light from that galaxy is being bent around these massive overdensities. And that's causing these arclets. They're just distorted image of the galaxy behind the cluster. Anyway, this is taking it to an extreme, but just to show you the sort of structures we see in the universe. Now, what Tony talked about yesterday, I presume would include this. This is the expansion of the universe, also known as Hubbles Law, where the recession velocity V, must look for a pointer. Is there a pointer somewhere? Well, I'll do it like this. The recession velocity V up there. Great. Thank you. The recession velocity here is proportional to the distance of the galaxy via the Hubble constant here, where the Hubble constant is 70 kilometers per second per megaparsec, roughly, plus or minus a few. And what it means is that if we assume this is us, then galaxies further away move faster away from us. And they're all moving away from us in a sort of radial direction, not because we are particularly unpopular, but because the whole universe is expanding as a whole. And every galaxy would, if we were here, we would see that all the other galaxies would be moving away from us as well. It's just from our point of view, they seem to be moving away. Now, the recession velocity, v, we can measure by taking a spectrum of a galaxy. So imagine this elliptical galaxy here. We take a spectrum. You'd see these absorption lines. This is magnesium-2. Normally, if we measure that line on Earth, it's at 5170 angstroms. An angstrom is 10 to the minus 10 meters. 5170, but actually we measured it around 5250. So it's shifted towards the red part of the spectrum. And that's because the galaxy is moving away from us. These lines get shifted to the red part. Hence the term redshift for these galaxies. So this is how you measure the velocity there. This is the sodium D line. The calcium line's in here as well. But it's much more difficult to measure the distance there. So normally people measure the velocity, assume a Hubble constant, and say, okay, this galaxy is at this distance. Now that, actually, I felt, the universe expansion is basically just like a cake in an oven that's rising, a raisin cake, and we are just one of the raisins. So as the universe is expanding, the raisins are moving further and further away from each other. I was just playing around there, so anyway. That is only true if the universe is homogeneous and isotropic. But on the local scale, I've shown you a picture of clusters. So you have these clusters of galaxies, or voids of galaxies, which perturb the local Hubble flow of galaxies. So if the Hubble flow is these sort of yellow lines here, then you can imagine a big cluster of galaxies by gravity inducing these vectors, these velocity vectors. The further away you are, the smaller the contribution is, the closer, the bigger. And in fact, the resulting motion of the galaxies is the sum of those two components. So in fact, this galaxy is moving in this direction, partly because of the cluster here and because of the Hubble flow as well. Now, one thing you must bear in mind is that we can only measure the radial component of that motion. We cannot measure the tangential motions. We can only measure the radial component of this vector. But anyway, if you do, if you now do measure the velocity of the galaxies, and you can somehow measure the distance to the galaxies, you can measure these peculiar velocities here. This is the peculiar velocity field due to these irregular mass distributions. And that will tell you about the underlying mass distribution. Anyway, if we can measure this somehow, and we can measure this from spectroscopy, we can determine the underlying mass distribution. Sure. The blue arrows here are just... Oh, here, it's VR, the peculiar velocity of this particular galaxy, for instance, as a function of r, minus our own peculiar velocity, so relative to our own motion, and only in the radial direction. So VR, V0, our own position. And that's the peculiar velocity field, basically, induced by gravity. That we are, in fact, moving relative to some rest frame is evident in the cosmic microwave background maps. This is an image taken by WMAP, which is the Wilkinson Microwave Anisotropy Probe. And this is something that's long been known. This is the plane of the galaxy here. But you can see it's brighter over there and fainter over here. This is known as the dipole, and it represents the motion of our local group of galaxies, the Milky Way, all the other galaxies in our neighborhood, with respect to the cosmic microwave background. And it's quite a significant effect. You would deduce a motion of our local group of about 600 kilometers per second to explain that dipole in this picture here. But if we look at the galaxies around us, the nearest group, the Virgo Supercluster, can only cause something like 200 kilometers per second. So there's something more out there that's actually pulling at us, but we don't really know what it is. What's causing that motion is one of the question marks. As a little sideline, the microwave background is also very interesting because if you actually subtract the dipole from it, you can see all these little fluctuations. And these are the earliest fluctuations that we can observe. Basically what you see here is the universe as it was at the era of recombination at the redshift of 1,000. And somehow we think that through gravitational instability, these little structures are what's now known as the clusters, the superclusters, and the large-scale structures. Anyway, but that was a little sideline. Actually, coming back to the distribution of galaxies and nebulae, this is a map made by Sir John Herschel back in 1834 when he was actually in Cape Town looking at the southern sky. And The colors are a bit difficult with the lighting, but the little green dots are here. The red dots are just nebulae in the galaxy. This is the plane of the Milky Way. This is all of the southern sky. And you have the Magellanic Clouds over here. Now, in this very early on view of the universe, back in the 1830s, you can already see clumping of galaxies, of the nebulae. This here is a very well-known cluster, the Centaurus cluster. There's a cluster here, and you can actually see a sort of wall-like structure over there of nebulae. This
the 600 kilometers per second is the size of
the dipole.
220 is the approximate amount you could subtract off for the Virgo cluster.
That's
in
right.
The same direction?
Roughly in the same direction. I mean,
so you could subtract it off and there's a discrepancy of 300 million.
Roughly, yeah. But there's more. I mean, I'll show you the other components to that particular. There are various components. There's a component. Well, I'm running ahead. I'll show you just now. Yeah. This, of course, is a picture that you probably recognize. This is Table Mountain, and this is where John Herschel had his observatory in the Cape here, from where he measured where he saw all these nebulae in the southern sky. And this is the picture as we know it now. The same part of the sky, you can very clearly see this wall of galaxies here, the Centaurus cluster up there very easily. And what you see here is the Milky Way running across. So behind the Milky Way, we cannot see the galaxies. They're there, presumably, or almost most definitely, but the dust in the Milky Way is blocking our view from what's behind, so we can't really see if this is indeed one big structure running across. And also note this is a two-dimensional projection. This is just the galaxies on the sky. It has no distance information in here. Okay, now coming back to the Great Attractor, the initial discovery was made in the late 80s by a group of people called the Seven Samurai. These were 7 people studying the peculiar motions of galaxies. And they found when they look in this part of the sky, this is roughly, again, the same part of the southern hemisphere. Now the Milky Way runs across here. And this is, again, that big structure with the Centaurus cluster here. It's just rotated by 90 degrees compared to the previous image. They found if you look in this part of the sky here, that all the galaxies here are moving too fast for their predicted distance. This solid line here is the uniform Hubble flow. So if all the galaxies were just following the Hubble flow, they would have all fallen on this line here. But in fact, they're all above that. They're all moving too fast for their predicted distance. And that was explained by saying that there must be a concentration there, causing an extra stream of galaxies. And this stream had a magnitude, roughly, of about 500 kilometers per second. And that would imply a mass of 5 times 10 to the 16 solar masses, roughly 20 times very massive clusters. So there should be 20 very massive clusters there that could cause that sort of pull. Now you can see it's very close to the Milky Way as well. So initially people thought they couldn't see the mass associated with the Great Attractor. They could see some clusters, but not enough to actually cause this streaming. And that's partly due to the Milky Way there. One more thing is what I said already earlier. If you can measure the distance and the velocity for many, many galaxies altogether, you can determine the underlying mass density field. And that's what's been done here by people also in the mid-90s. Basically, they've taken a peculiar motion, and they've then reproduced what the underlying mass density field is at a given distance. So this would be a distance of 4,000 kilometers per second. I'm using distances and velocity sort of one in one. But at a distance of 4,000 kilometers per second. And this whole extended region on the sky is what's known as the Great Attractor. On the other part of the sky, 180 degrees away, is another concentration called the Perseus-Pisces overdensity. But that one is very well mapped. People have known for about 100 years that there are many, many clusters there. This is the Great Attractor here, and this is the plane of the Milky Way. So they, in fact, find the center of the Great Attractor right behind the Milky Way. And that's why this is just another representation of the Great Attractor when you look inside what's known as the supergalactic plane. So if you look at galaxy distribution, they preferably lie in this plane here on the sky. And if you take a slice of that, you can see, again, the Great Attractor overdensity here. So what of the Milky Way? This region of the sky we call the zone of avoidance, not because galaxies aren't there, but just because galaxies appear to avoid this region of the sky. And this is just the Milky Way, an optical picture of the Milky Way here. Galactic center roughly here. And this is the region of the great attractor. So somewhere behind there is the center of the great attractor. And you must just imagine that we are part of this galaxy, and you just look through a thin disk of stars and dust, all in our line of sight. And what's the effect of what it has on the appearance of a galaxy? It will make it smaller, and it will make it fainter. So if there's much dust in the galaxy and we look through it, this very big spiral galaxy here, if you put what we use 10 magnitudes of extinction, it's a bit awkward, I hope you can see it, becomes much redder and actually much smaller as well. But it's not only the dust, it's also the stars in the galaxy that will make the galaxy disappear. So what was a very big, bright, obvious galaxy here suddenly becomes a very faint smudge. And it's very hard to find these galaxies, even though they're intrinsically, this is just a simulation, of course, but intrinsically it's a very big galaxy there. Or check this one out, there on top. Behind the Milky Way, you can hardly see them. There's something here, and there's something there. So it's very difficult to look for galaxies behind the Milky Way. And very easily, a concentration of galaxies like the Great Attractor, or parts thereof, can be hidden by the Milky Way. So we've looked for smaller galaxies behind the Milky Way in the optical, as part of my PhD thesis, in this part of the sky. So this is where the Great Attractor is. In these two regions, we looked for galaxies. Now, the yellow dots here is what was known before the survey. People have done an all-sky survey of galaxies larger than 1 arc minute. So they take a diameter size, and they find everything larger than that to be complete to a certain size. But coming closer to the galactic plane, or from this way, you start losing the galaxies because they become smaller and smaller. So we looked for smaller galaxies in that part of the sky, and we found a whole lot, 8,000 new galaxies that were there, that weren't seen before. Now, these aren't intrinsically small galaxies. They're only artificially small because of the extinction. And what you can see very close to the Great Attractor Center, we find this big concentration of galaxies. By far the strongest overdensity of galaxies in the search area. And this is associated with a cluster of galaxies, Abell 3627. And if you look at that on the sky, it takes a little bit to download. If you look at that on the sky, this is a picture of that. I've got the size of the full moon here. That basically represents the full size of this image. This full size of the image is the size of the full moon. It's half a degree by half a degree on the sky. And what you can see, this is now centered on that concentration, is many elliptical galaxies here. There are in fact 500 galaxies just in this picture. And also 250,000 stars, because we're looking through the Milky Way. I can zoom up a little bit. You can see here, these are the 3 big, bright ellipticals in that galaxy cluster. The other galaxies here, smaller galaxies there or up there. And in fact, I can zoom a little bit more. And this is this very central galaxy here with many smaller dwarf galaxies. So it really is a rich cluster of galaxies. But again, this is just a projection on the sky. We don't know the distance yet, or the recession velocity.
Is it an ESO picture?
I've actually taken this picture with a wide field imager, but it's been an ESO press release as well. Back.
Which telescope do you use?
This is the 2.2 meter telescope, with a wide field imager on. I don't know if people talk to you about CCD cameras and so on. This is a combination of 8 CCDs that gives you a very large field of view. Normally, you've got a much smaller field of view. But the wide field imager has the ability to actually map half a degree at a time on the side. So there are many, many galaxies there, but we don't know the distance. So in order to get the distance, we've got 3 telescopes lined up, or we had 3 telescopes lined up. One in Chile, the 3.6 meter telescope, the 1.9 meter here in Sutherland, in South Africa, and the 64 meter Parkes radio telescope. I don't know if you've seen the movie The Dish, but that's this telescope here. And each of these telescopes have their own little niche areas. We've used this telescope to look at clusters, because this particular setup had this telescope had a spectrograph that could look at 25 galaxies in one go within a 1 degree field. So you look at dense regions with this telescope. We looked at bright individual galaxies with this telescope, because of the slightly smaller aperture as well. And we look at gas-rich spiral galaxies with the radio telescope. The radio telescope is probing the gas in the galaxies. So you wouldn't look at elliptical galaxies because there's very little gas in elliptical galaxies. So spiral and irregular galaxies are the ones to follow up with that. Now what you get then is, this is the distribution on the sky now. We've merged our galaxies in the all-sky distribution, and you can see that before it was largely empty. Now we can trace the galaxies much closer to the galactic plane. And what you can also see as a function of distance here is that in the great attractor region, which is this region here, there's a very strong peak just at the great attractor distance, which is associated with that cluster that I've just shown you, that picture on the sky. All the galaxies in that region are peaking very strongly at 5,000 kilometers per second, which is where the great attractor is. If you go to this region on the sky, you can see a very broad overdensity, roughly centered on the great attractor. And if you go even further away, you suddenly see that large-scale structures are very different there. There's no strong peak at 5,000, so you're probing different large-scale structures in these different regions here. And very clearly in this region where the great attractor is, there's a very strong peak at the distance of the great attractor. Now, I think a picture like this would have been shown yesterday by Tony Farrell as well. This is just, I call local cosmography. It's just to get a feel of the local universe and the structures in there. I've put in megaparsecs, but if you want, you can also use kilometers per second. This is from 0 to 1,000, from 1,000 to 2,000, 2 to 3,000, 3 to 4, 4 to 5, 5 to 6,000. And these two panels here is the great attractor distance. And the great attractor is roughly located here or there. So you can see the clusters, the Centaurus cluster or other clusters there. And this is where this new cluster is, behind the Milky Way. Right in where this whole large-scale structure of galaxies is located. Now, one thing that's interesting to know in this particular picture is that this particular wall of galaxies that runs across here is also seen here, is also seen there. This is the Virgo cluster and its association there as well. And basically what you see is a wall of galaxies seen edge on. So at all these distances, you see this wall of galaxies running across roughly here and here. So you have these slices through this wall of galaxies as you look out. And roughly at the great attractor distance, this whole structure is here. I mean, it's hard to see here in the optical because we do not find the galaxies right behind the Milky Way. But actually more galaxies have been found with radio techniques and other techniques. And there's a big large-scale structure here. And where this wall here intersects with that wall is where the great attractor is. As if it's at a nodal point between large-scale structures is where the cluster is.
This gives you the feeling of bubbles.
That's right. Oh, absolutely. I mean, you can... it's maybe a little bit hard to see, but you can see these sort of little voids there. In fact, in the walls itself, you've got smaller voids as well.
We're part of the Virgo.
Yes. Yeah, actually, Virgo is part of this whole structure as well, and we are actually on part of that as well. So it's us, Virgo, great attractor, all into one sheet of galaxies with small little voids and bubbles. I mean, there's these little voids within these structures as well. Again, this picture I've shown earlier, this was a slice through the supergalactic plane. In fact, maybe I should say, that this here is largely corresponding to the supergalactic plane, that whole wall of structures there. That's what people use to define the supergalactic plane. Now, this new cluster is here. And you can see the cluster. It's a cluster, it's a rich cluster, because it's elongated like this. And that elongation is called the finger of God effect. And it's not really a finger of God, and it's not really an elongation. What happens is, if the cluster is so massive, the galaxies in the cluster will move through the cluster. And if it's very massive, they will move even faster. So the more extended this is, we are at the center, the more extended this is, the more massive the cluster is in a way. The faster the galaxies move through the medium. This is the Centaurus cluster, a well-known cluster, Pavo cluster. And this now here is this cluster very close to the center of the great attractor, which has an enormous finger of God effect. So it's the most massive cluster within the great attractor over density, but a cluster like this on its own cannot explain the whole motions of the great attractor. It's too small for that. It does generate local streaming motions, but not on the scale we're talking about here with the great attractor. Anyway, it is the most massive cluster in the great attractor over density. Now, one thing I'm particularly keen to find out is to actually measure the distance to the cluster and see what the cluster is doing with respect to the cosmic microwave background rest frame. Because if the cluster is really massive and it resides at the center of the great attractor, you don't expect it to move through space at 600 kilometers per second. It will be at rest with respect to the cosmic microwave background. And if we can somehow measure this distance, and we've already got the velocity, we can measure the peculiar velocity of the cluster as a whole and see how it fits in within the great attractor over density. Now, that's very difficult for many, many reasons. Not in the least that peculiar motions have never been, this is called peculiar motion, to measure that difference between the velocity and the distance. This has never been measured behind the Milky Way because it's very difficult. You need to correct for the extinction, you need to correct for the diameter reduction of the galaxies. It's very tricky to do that, but it's very important to find out what the great attractor is really about. Actually, how do you measure distances to galaxies? So how do we determine this? One way is to use supernovae as modified standard candles. There is a certain kind of supernova, type 1As. I guess someone will talk about it during the summer school, or if not, someone should actually talk about this. I won't spend much time, but these have been used recently in the last 5-6 years to actually measure the geometry of the universe by measuring these supernova explosions very far out, roughly halfway across the universe from us. So that's one way. Or one way that we actually use is the fundamental plane of elliptical galaxies. I'll explain both here. The supernovae, the principle is that for an object of standard intrinsic brightness, if you measure the brightness for it, you can get a distance. The fainter it appears, the more distant it is. That gives you this relation, the distance modulus, and it's a function of the distance. But the problem with the supernovae, they're not exact standard candles. They vary slightly in terms of peak brightness as a function of the shape of the light curve. But if you can measure the shape of the light curve, you can make them standardized candles. And this is an example of a supernova in a galaxy here, 4526. Also a picture of the HST. And for a certain kind of supernovae, the thermonuclear runaways, you can actually use them. And they've been seen up to 8 billion light years away. And you can measure them because they become intrinsically very, very bright. This is just to show that picture. This is now redshift as a function of the magnitude difference compared to various models. And the basic evidence for a cosmological constant is what they deduce from this, is that all the supernovae far out here were all a little bit too faint, 0.2 of a magnitude too faint to the then standard models. And they could only explain that by invoking a cosmological constant. And this model runs across like that, and you see that further out, the galaxies, the supernovae, become brighter again. And that's because in the early universe, it's not cosmological constant dominated, but it's still dominated by the matter density. Anyway, this is a sidetrack. I want to keep short because it's sidetracking a little bit from what I'm talking about. This is just to show the problem with the supernovae for our particular work, because we're looking through the Milky Way. There are many, many stars in our own galaxy there, so it's very hard to find a supernova in this particular galaxy to then follow up and measure the distance to the cluster. It's doable, but it's very tricky, and you need lots of telescope time to follow that up. I'll come to star subtraction in a minute. It's actually possible to subtract all these stars to actually derive the brightness of this galaxy, but it's very difficult. An easier way is what we use is the fundamental plane of elliptical galaxies. Now what you use here is a 3-parameter relation between the motions of the star and the galaxy. The faster the stars move within the galaxy, the more massive the galaxy is, and that relates to the brightness of the galaxy, and if you assume a constant mass-to-light ratio. The size of the galaxy and the brightness of the galaxy. This is the motion of the stars. That's the brightness of the galaxy, and this is the size of the galaxy. And you can see for individual clusters, this is the Coma cluster, it's quite far away. The Virgo cluster is nearer to us. They form a very tight relation. And the different intercepts here, you can see this one is slightly different from that one, by one sort of unit here, or half a unit there. The different intercept is just a relative different distance between the clusters. Yeah, you measure relative distances between the clusters if you measure this relation for any given cluster. Now you must measure many, many galaxies, because for one galaxy alone, it gives you a distance accuracy of about 18%. So at the redshift of the great attractor, you can have for one galaxy a distance accurate to about 1,000 kilometers per second, which is much larger than the peculiar velocity of the great attractor, which is 600 kilometers per second. So if you really want to have it accurately done, you need about 60 galaxies. You beat down on the uncertainty. You get 18% divided by square root of 60, and you get an uncertainty of about 100 kilometers per second, which is much lower than the peculiar velocity that we talk about. Anyway, problems, plenty of problems. We must know the exact extinction. So how much dust is there in our line of sight? Because this is what we measure for these galaxies, but we need to know how intrinsically bright the galaxy is if we want to compare it with other clusters away from the galaxy. And the other problem is stars. There are many, many stars on top of the galaxies, and we need to subtract them. Luckily, you can do this very accurately if you model the shape of the star. That's very well known, and you can use the computer to do that. And I've got a little animation, no PowerPoint presentation without a little animation. You can slowly see the stars disappear here. It's actually not quite, I haven't quite finished this yet, but you can continue running this until all the stars disappear. And you need, to actually do this job properly, you need to do lots of simulations as well. Add artificial stars to your galaxy, subtract them, and see the difference in brightness, which is one of the things I'm doing at the moment. Anyway, this is where we are with the Great Attractor. It's the most massive nearby superclusters. There are more massive superclusters, but this is the nearest one of them. And its center is marked by the nearest rich cluster of galaxies, this one over here that I showed the picture of, Abell 3627. But still our view of the Milky Way is very much hampered by dust in the Milky Way. And there are in fact many more clusters still in this region of the sky. And this is just 2 galaxies that are located here around what we suspect is another cluster in the Great Attractor. And for that sort of, if you really want to look very close to the galactic plane here, you need infrared observations or even radio observations where you can penetrate the dust much better than in the optical. We've got a very nice infrared telescope, in fact, in South Africa, a 1.5 meter survey telescope built by the Japanese, and it's been used now for the last 3 years. Now, one of the questions here is, how do large-scale structures form? This is a big mystery still, a little bit of a black box. How do we come from these initial fluctuations at the imprint of the earliest view that we have of the universe to all these large-scale structures that we see around us nowadays? And one way that we think we can solve this or tackle this is with SALT, our own 10-meter big telescope here, which is being built at the moment. SALT will be able to address issues like structure formation, of a large-scale structure formation, and will be used for these studies of peculiar motions. So I guess someone is talking about SALT as well as part of this whole course, and if they're not, they should, actually, because this is where astronomy is going in South Africa beyond this year. It's almost ready. They've finished, they put on the whole tracking unit here. I don't know if someone is going to talk about SALT. Is there anyone who's talking about SALT or not? You don't know? Then I'll explain it a little bit. It's a slightly different designed telescope in the sense that it can only move around one axis. It's got a fixed angle of 35 degrees looking at the sky, and it can only rotate around that angle. It can only rotate around this axis here. And then it sort of goes around like that. This is roughly 10.5, 11 meters, but you don't always illuminate the whole mirror, depending on where the object is in the sky. And what happens is that as your object moves across, the secondary telescope is actually following the object as it moves across the mirror. And this whole unit has been put in place a few months ago, and they've already had first engineering light of the telescope. And the whole of this year is going to be used to actually commission the telescope. So by the end of this year, people will actually use the telescope for science. This is where it is. This is Sutherland. This is the 1.9 meter telescope that I've talked about earlier. This is where SALT is going to be. And these are the other telescopes. This is the infrared telescope there. And that's SALT again. There's a website here, www.saltacza, where you can see more pictures of SALT actually being built at the moment. This is just a picture, actually quite an old picture. There are about 20 mirrors in at the moment. Here there are 90 or 19. This is an earlier picture where there were only 7 mirrors in. And one of the nice things is that each of these mirrors are sort of 1 meter diameter. And they've got edge sensors in between. So then each mirror will know where the neighboring mirror is. And so they can keep the shape of the mirror. One thing I should have said is this is a spherical shaped mirror, unlike the normal telescope. And on the top they've got a spherical aberration corrector, which corrects the optics for spherical shape. This again is a sort of layout. This is where some of the instruments will be on top. And this is the hexagon of 91 individual mirrors. So in the course of this year there will put in more mirrors until they've got 91 early next year. So that's very exciting, and I want to finish up with one thing I'm involved in is the virtual observatory. More and more virtual observatories are coming around in the world, and you can see South Africa is a big gap there in the whole distribution of virtual observatories. A virtual observatory is nothing else, well, it's a glorified version of a data archive, but in a data archive which can cross-correlate between various surveys, various wavelengths of surveys. And I've found a nice acronym. I don't know. Astronomers love acronyms. So ours will be called Avocado, which goes very nicely with SALT as well, which is the African Virtual Observatory, basically. This is very much in its early days still, but we've got so many facilities here that generate huge amounts of data that somehow this must be coordinated, archived, and so that it can be used again and again for different purposes. So hopefully in the next few years this will develop and become one of the resources that we have as well. And I think I'll leave it at that. Thanks. Questions?
I don't explore the geometry quite right. Virgo is not antipodal to the attractor. The attractor's in center.
Yeah. Virgo is roughly 90 degrees away.
90 degrees away.
Yeah.
Okay, so that would produce a quantum motion.
Yeah, Virgo, well...
Produce some small amount of motion, 20 kilometers per second,
yeah.
in a perpendicular direction.
Well, the motion that we have, if you put it in... yeah. if you can put it in Cartesian coordinates, in which you have the supergalactic X, Y, and Z frame, for instance. The supergalactic X and Y... Sorry, let me close it for you. Supergalactic X and Y, the motions are quite well understood. You've got Virgo, you've got the great attractor. Supergalactic Z, we don't know. There's still a component missing there of about 200 kilometers per second that we don't know what's causing that. X and Y we do know. That's the Virgo cluster and that. But the 600 kilometers per second of the dipole is just the combined factor of X, Y, and Z.
Yeah. So there's a vector addition problem.
Yeah.
But the geometry just wasn't very clear.
Let me go back to.
That's fine.
That's one. The other thing is that I want to show is that we've got the great attractor here. We've got Perseus Pisces on this side as well, which is on the opposite side. And the only reason why we think we're moving towards the great attractor and not Perseus Pisces is that between us and Perseus Pisces, there's also a big void of galaxies, whereas from us to great attractor, it's a continuous coverage of galaxies. There's no big void in between us. So,
It's about 100 megaparsecs.
roughly, yes, yeah, roughly, yeah. But basically, you can see the universe structure. You've got these walls and bubbles and so on. There's not like a nice isotropic homogeneous locally, and this up here is the Virgo. So from there to the great attractor is roughly 90 degrees on the sky. Yeah. Any other questions? That's fine. Thank you.